So I don't really have a pitch. I have a story that I want to tell about trying to use zero-knowledge proofs in a practical setting. So one thing that I think about a lot is designing signature schemes that are not very fragile to like engineering considerations. So an example of that is y'all are probably familiar with like DSA or Schnorr signatures or something. These are linear equations in two variables. Two secret variables, I should say. One is your secret key, one is this ephemeral secret key we call a nonce that you produce for each signature. And in practice, when you're generating these signatures, you need to generate a fresh, uniformly random nonce for every single signature. If this is biased in any way, even by like less than a bit, there are attacks. You can gather up many signatures, put this into some sort of lattice, do some basis reduction, and actually solve the series of linear equations and get all your nonces and your secret key. If you reuse a nonce, you can directly solve, right? So every signature is one equation in two secret variables. If you reuse a nonce, now you have two equations in two secret variables. Anyone can solve for them. That kind of thing. So people, if you try to use a random number generator, you're susceptible to any problems with your RNG. If there's a hardware RNG, you have to trust that it's working properly. If you have a software RNG, there's been a long history of various problems with that. So there's sort of a best practice these days. Rather than using an RNG, you use, there's an IETF, or RFC 6979. You deterministically generate your random nonce from your secret key and the message that you're signing. And that way you will get a uniformly random output that is always the same if you're signing the same message, but will always be different if you're signing different messages. And since the message and your key and your public nonce are everything that goes into the hash, which is a coefficient of your linear equation, the result is that you always have one more secret variable than you have linear equations. Nobody can solve for your stuff. That's great. The problem comes in when you try to extend this to working with multi-signatures. With Schnorr signatures in particular, there's a way that you can do multi-signatures where everybody sort of creates their own signature on sort of this modified message hash, where you're hashing not only your own nonce, but everybody combines their nonces and you hash this. And then everybody adds their partial signatures, is what they're called, and they get a full signature, which is a signature on this joint key that everybody owns. Now, if somebody is doing this and they try to generate their nonce deterministically in the way I suggested, then there's an attack someone can perform on them. Specifically, the attack is somebody will go through the signature protocol. They'll get a partial signature from the mark, and then they will abort. And then they'll come back, give a different nonce, and then redo the same thing. So the attacker has changed their nonce. The attacker has changed the message hash, but the victim has not. The victim is using the same secret nonce. So the victim's partial signatures then form a system of linear equations of two secrets. The attacker can take those two partial signatures and solve for the secret key. Okay, so there are a variety of solutions to this. You can use an RNG that has all the problems that I listed. You can add a counter into the deterministic hash that has problems with like state resetting or like forking your VM or forking your process. You can stick a wall clock on there, and then you need an RTC and all this. There's all these sort of fragile solutions. But there's a solution involving zero-knowledge proofs, which we all like. Those are our favorite solutions. What this is everybody at the first stage of the protocol, when they choose their secret nonce, they provide a zero-knowledge proof that they did the RFC 6979, or maybe something that's a smaller circuit or something. They do a zero-knowledge proof that they generated their nonce deterministically. And this means that an attacker who wants to try this, wants to run the protocol forward, abort, come back with a different nonce to change the message hash, they can't, because they are required to provide a zero-knowledge proof that they generated their nonce deterministically. And this solves the problem. As long as this determinism means that every invocation on the same message, which is the same counterparties, results in the same nonce, then you're great. So I tried to do this a couple weeks ago. I was all excited. I had implemented bullet proofs, which are a type of zero-knowledge proof that you can implement on any elliptic curve, and that works very well with committed values and public keys. I implemented this for my favorite curve with my favorite signatures. And I needed a hash. I needed to do this deterministically somehow. So I asked Peter, I said, Peter, I need a SHA-2 circuit. And he said, and then he asked Sean, and Sean said, oh, use the one from JSNARK. So Peter went to the JSNART code, he like ran it and pulled some intermediate files out and then somehow extracted a bunch of equations from this, and then he turned that into this domain-specific language, which he then ran some sort of dynamic programming thing to optimize all these linear constraints in a way that would provide a very efficiently producible proof. And then I took that and then I hacked it all up and like transposed some matrices and made some of these constraints implicit and stuff so that it would work efficiently with my code. And the result was that I had this deterministic circuit. It was about 65 kilobytes of stuff, you know, that was sort of onion routed from the SHA-2 function, and that people would be expected to use. And as long as it's sound, then no one can get their keys out. So of course, this like I don't even trust this, and I implemented it. So we got to thinking, like, how could we do this in a trustworthy way? Like here we have this kind of ridiculous series of events that led to this circuit, but even in general, how can you prove that a circuit is functionally equivalent to something legitimate? And I don't know, and then there's some difficulties here. So one thing is maybe we could have a deterministic compiler to circuits, but there are non-deterministic parts of what we did that are important. So like when Peter was optimizing these linear constraints, that's a very non-deterministic thing. Although it's also, every step was very simple. Maybe he could produce a witness for each step that he did every time he arranged two things. So maybe there's a combination of deterministic compilers and compilers that produce witnesses for every step that they do to prove that they didn't change anything. I don't know, but there's not really any tooling for this. And when I looked around to like how could I actually make this system practical, I realized there was this big open question about how do you make zero-knowledge systems that have large, complicated circuits in a way that you don't basically have these binary blobs of closed-source circuits that nobody can verify. And I just wanted to tell this story because I got all excited about zero-knowledge proofs. These are the future, like we can do anything. And then I tried to do it, and I ran into this wall. And I hope that people in this room will think about it and yeah, I was trying to do it in the present, yes. It's very difficult for me to do it in other times. So yeah, so maybe that was my only issue. I just need to try harder. Because I know if you yeah, well, if you move fast enough, you can get there pretty quickly, I hear. So yeah. So, but that is my story. That's what I wanted to tell. So I hope you guys will think about that and maybe help me out and come talk to me.